Hello, I've been asked to do a couple of questions from the homework for 4.3. Those will be questions 34 and 43. I'm going to come back to 34 after I've done section 4.5 because we're going to do a very similar question in 4.5. But I will jump down to question 43, which looks at the parachutist who's falling, who is in free fall at a velocity of 136 kilometers an hour. So if I draw the free body diagram for that person. So there they are, in free fall, right, traveling down at a constant speed of 136 kilometers per hour. I'm going to convert that (1,000 meters is 1,000 meters is a kilometer, and 1 hour is 3,600 seconds. And my kilometers disappear, and my hours disappear, and my kilometers disappear, and I'm left with meters per second. Okay, and the answer is 37.8 meters per second. Now, if you actually look at the answers in the back of the book, mine might vary a little bit. So you'll see as we work through this that there's a method to my madness. I'm going to use a sign convention. Anytime I have up-down motion, where not all of the numbers are going to be in the same direction, I assign a positive direction and a negative direction. So in this case, I'm going to assign the up direction as positive and the down direction as negative. Now, if I look at the forces that are being applied to this person, I have a gravitational force, which is 686 newtons. And I have an upward force. When she pulls her parachute, the air starts pushing her up, which is slowing her down, right? She's got velocity going down. Maybe that's terminal velocity, which means at that point in time, she's reached the fastest that she can possibly go, because as the planet is pulling her down, the air is pushing her up. That's without the parachute. Then the parachute pops open and she slows down. Why does she lose her downward speed? Because the air is pushing up on the parachute. So the air pushing on the parachute creates a new resistive force of 895 newtons. Okay, so now that I have a force of air resistance and a force of gravity, I can look at what is the net force acting on this parachutist at this point in time. The F net is going to be plus, let me erase those. F net is equal to the plus 895 plus the minus 686 because of gravity. So the F net is going to be plus 203 newtons. Okay, what that's telling me is the net force is actually pushing her up, which is why she's going to slow down as she's falling. I know F net is also equal to MA. And I know that her mass is 70 kilograms. And so the acceleration for this person turns out to be plus 2.9 meters per second squared. Right, it's a positive answer because I have a positive force, an upward force, indicating that she's accelerating in the upward direction. You think, how can she be accelerating up? Well, she's accelerating up because she's losing downward velocity. If I was originally going at, say, 200 kilometers an hour, and now I'm traveling at 100 kilometers an hour, what happened to me as I'm falling? Well, I'm going to lose downward velocity, right? Negative, losing negative, which means I have positive change in velocity, which means positive acceleration. So my acceleration here, which is a vector, just like F net is a vector and Fg is a vector, and all these are they're all vector quantities, right? The acceleration is up at 2.9 meters per second squared. In the book, they say she has negative acceleration, meaning she's slowing down, which is true if you assume that the direction of her motion originally was positive. If that's the case, then all these numbers become the other way around. If up is negative and down is positive because that's the direction she's going, then the FG becomes plus 686. The F net becomes negative 895, and her net force becomes negative 203 newtons, meaning her acceleration would be negative 2.9 meters per second squared, which in one way makes more sense to say that she's decelerating, losing speed, but that's only if the direction that we've chosen is the positive direction. We often do that when we're doing physics because we say if an object is going this way, this way, we might say this way is positive. If an object is going this way, we choose this way as positive. If an object is moving this way, we might choose this way as positive. All right? But in this case, because of the up-down motion, I like to use up as positive and down as negative, which means the positive acceleration that I have here doesn't mean she's speeding up. It means she's losing negative velocity. Right? Losing negative, 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 right? Which means positive acceleration. Okay, so there's part of probably what is the problem with the answers that seem to be in the back of the book. And then it says, how far will she travel during that time? Well, if I do a delta D equals V1 delta T plus 1/2 A delta T squared, I can find her displacement because I know her initial velocity was 37.8 meters per second. Oh, that's 37.8 meters per second down, which is negative 37.8 meters per second. So when I come back down to my question here, V1 is negative 37.8. It says she's going to experience 5 seconds of this slowing down, plus 1/2 of her acceleration, which was plus 2.9 meters per second squared, times the time that she is slowing down, okay, which is 5 seconds squared, and I'm getting a delta D of negative 153 meters, which makes sense because she's actually going to travel 153 meters down in the time that it takes for her to lose that speed. I think, well, I wonder what's actually going to happen to her in that time while she is falling. So that's the answer to the question, right? The question was asking, what is her delta D? What is her displacement? Right? But if I also want to know, I wonder if she was traveling down at minus 37.8 meters per second, when she pulled her parachute, what will be her speed 5 seconds later? Well, if I know that she started at minus 37.8 meters per second, again, this isn't part of the question, but I was just kind of curious, plus 2.9 upward acceleration, right, losing negative speed, times the time that she's going to be slowing down, 5 seconds, I get an answer of minus 23.3 meters per second, right, which is 84 kilometers an hour. 23.3 meters per second down, or 84 kilometers per hour down.